Hi everybody. Welcome back to the second part of the NMR lecture. I'm going to start this lecture by drawing an NMR instrument. So NMR spectrometer. Um, so I'm going to do my best here to draw an NMR tube. Those guys are really slender and long, but I'll do my best. Oh, that kind of looks like an NMR tube, right? So here we have our NMR tube. And our NMR tube sits inside this thing called the solenoid, right? The solenoid is in the magnet. Okay, so it's basically the big the superconducting electromagnet that the NMR tube sits in. We'll talk more about that in a second. And then also down here, our samples right here, by the way, at the bottom of the NMR tube. But down here, the NMR tube, there is around the NMR tube is a coil, right? And then this is the RF coil, or the radio frequency coil. And the radio frequency coil is responsible for both pulsing the sample with radio frequency, but also detecting the output, or the signal that comes from it, the current that comes from the coil. And so this is the RF coil. And then this is the solenoid inside the magnet. In the magnet, okay? So the RF coil then is, of course, connected to an amplifier. Right? Which amplifies the signal coming from the RF coil after the pulse. And that signal gets amplified and sent to an analog to digital converter. Analog to digital. Analog to digital converter, right? Also known as an ADC, right? And then that digital signal coming from the analog to digital converter is sent to a computer, where the output can be visualized, right? So this is our computer with the output. With the output, okay? And just like I was saying before, if you're my generation, you have a computer with the output. If you're like Generation Z, then you have an iPad or something like that. But for Dr. Pelfrey's generation, what they actually had was paper. And what they would actually do is the paper was sitting under a pen, right? And whenever the signal came out, the pen would move back and forth like this, like the kind of thing that you do with like a Richter scale for an earthquake. And that's how they would, or maybe even a polygraph, and that's how they would do their output or their NMR spectra with paper. Yeah, he's old. Tell him I said that. Anyway, it's important to know that if we imagine that the NMR spectrometer has a coordinate system in it, where we have the z-axis, the x-axis, and then the y-axis over here, right? The magnetic field, right, also known as B naught, is in the z direction, right? Direction of magnetic field right? And that's along the z-axis. That's along the z-axis, okay? So as I was saying before, The magnet that's inside of modern NMR spectrometers are not just magnets, and they're not just electromagnets. They're actually superconducting magnets. And so, even though our NMR isn't like that, our 60 megahertz isn't like that, but if you have anything that's higher field, anything like a couple hundred megahertz and bigger, those are all superconducting magnets. What does it actually mean to be a superconducting magnet? It means that the electromagnet has been cooled down to liquid helium temperatures so that there's a very minimal amount of resistance, right? And so the magnet becomes superconducting. That makes the magnet much stronger than a normal electromagnet, right? And so that's how we're able to get these huge numbers of Gauss that you saw in the previous lecture, right? Which corresponds to things like the 500 megahertz or 600 megahertz NMR or even a 1 gigahertz NMR, right? Because these NMR spectrometers, they really push the limits and they get bigger and bigger and bigger. Because, for example, the one I used was as tall as 2 stories, and you'd have to climb up a ladder to load the sample. The biggest one actually is 2 stories tall, and you'd have to walk across like a sky bridge to actually load the sample inside the building. I think they have one of those at Texas A&M. But they're very large, and the reason why they're large is because they need more and more helium to keep them cool, right? So that's what it means when we have a superconducting magnet. So let's write that down so that we're clear on what's going on with these, how these instruments actually work, right? The superconducting magnet is cooled by liquid helium. Which liquid helium is super, super cold, right? Which surrounds which surrounds the solenoid. That's inside the magnet. That's in the magnet. Okay? So to keep the helium from evaporating, there's a dewar that surrounds it. Right? So surrounds a dewar surrounds the liquid helium. And if you don't know what a dewar is, it's just basically a double-walled flask, right, or one of those tumblers, like a Stanley tumbler that's double-walled, and it's got a vacuum inside to minimize any kind of heat transfer, keeping the helium as cold as possible, keeping heat out and keeping the cold in, right? Surrounds the liquid helium. But that's not enough because that dewar is then surrounded by liquid nitrogen too to keep it cold, which is surrounded by liquid nitrogen. And then to keep the liquid nitrogen from evaporating off, right? Because liquid nitrogen helps keep the helium from evaporating off, right? To keep the liquid nitrogen from evaporating off, that's also surrounded by another dewar, which is the reason why these instruments get so big, right? Which is surrounded by another dewar to prevent evaporation of the liquid helium. And the reason why we care about that is because liquid helium is actually super expensive. It's super cold, number one, but it's also super expensive. And so when I was the NMR TA, basically the NMR technician at Auburn University, we would have to go and change or not change, but refill the helium about once a month. And every single time we did that, it cost like $1,300. And that was back in like 2016. So it's almost 10 years later. Helium is probably even more expensive now, which is actually kind of counterintuitive because or helium in itself is the second most abundant element on the universe, right? Because hydrogen is the most, helium is the second most abundant. Um, so why is it so expensive? Well, there really isn't a process that we can use to make helium, and so most of the helium that we have, that for everything from from birthday balloons to party balloons to like a blimp to the liquid helium that we use in NMRs, right, is actually mined for. And when you mine for it, right, helium is, at our standard temperature and pressure, helium is a gas. And so when you mine for it, a lot of it just kind of just dissipates into the atmosphere and goes into the universe. It doesn't stay on Earth. So it's really hard to mine. And so that's why liquid helium is so expensive, um, super expensive and super cold. So we would change out, or we would refill the helium on our NMR instruments about once a month, and then we'd also, because the nitrogen evaporates as well, even though it's inside of a dewar, it also evaporates, and that is changed out once a week, right? So liquid helium once a month, liquid nitrogen once a week, and it was a pretty important job because without having the what we call cryogens, those are both called cryogens. If we weren't doing any cryogen maintenance then on the NMR, we wouldn't have a superconducting magnet anymore, and you wouldn't have a high field magnet to do your NMR studies, right? So on the same note, this superconducting magnet has to be capable of making a very uniform and homogeneous magnetic field, because you don't want to have any kind of discrepancies or or irregularities, right, or anomalies in your sample. It will really mess up your spectrum. So magnetic field must be incredibly uniform, right? But the funny thing is that even though these magnets are super expensive, but did I say that? I think I may have forgot to say that. I said that the helium is expensive, but I didn't even tell you how much the instruments are. Um, a a 600 megahertz is probably around like 1 million or something like that. So a 1 gigahertz around 2 million, something like that. So they're pretty expensive. And so these super expensive superconducting magnets, right? They're pretty good at making a pretty uniform magnetic field, and a strong one at that. But even then, there's still some variation. And so to ensure that the magnetic field is homogeneous and uniform, we perform this operation called a shimming, right? So shimming is also required to help maintain a homogeneous magnetic field. Homogeneous magnetic field, right? And so I'm not sure if they do shimming on the instrument that's in our lab, which is a 60 megahertz, because they don't even that 60 megahertz is not even superconducting, and I'm not super familiar with the 60 megahertz that we have because, like I said, I'm more familiar with the high field instruments. Um, but shimming is definitely a thing that you have to do, especially when you get to the big instruments for sure. And so what happens? What exactly is shimming? Well, shimming actually uses smaller electromagnets, and that's in addition to the superconducting magnets that's already there, right? They're used to maximize magnetic field homogeneity. Homogeneity, right? So how does it do it? Well, it adjusts the magnetic field in the z-axis, x-axis, and the y-axis. I don't know why I wrote out the word y there. And I think my dog is like sleeping or something, making some crazy noises. Let me see. What are you doing, Tara? Calm down. The y-axis. Most commonly, though, right, it's really only the z-axis that's being adjusted, and this is known as z1 and z2 shimming. Most common. Oftentimes, too, the instrument will do it automatically for you. You just tell it to shim, and it will shim it automatically. You don't have to do it manually. I think sometimes with the older instruments require you to do it manually. So after that happens, right? Uh, After all that happens in the magnetic field, we get to this part here, where we are talking about the amplifier and the RF coil, right? And so here, in the amplifier, is attached to the RF coil, and is used to send an RF or radio frequency pulse to the sample. And is also also used to record the resulting signal which in this case is a varying voltage, which in this case is a varying voltage, which we'll discuss that more in a second, right? And then the last part here, which is the same for every other instrument that we use, the signal is converted from analog to digital signal. The signal is converted from an analog to a digital signal, which can then be visualized on a computer screen, which can then be visualized on a computer screen. And if you're a Gen Zer like yourself, then you'd have an iPad. And if you're Dr. Pelfrey, you'd just have this roll of paper. That is like really, really, really old school. Really, really old school. All right, so that takes us to talking more about the next topic here is going to be more about the energy differences that are involved in NMR spectroscopy. Okay, we talked a little bit about it before, but we're going to go into a lot more detail now. Okay, so more on the energy differences. Differences. I feel like my handwriting gets worse on the iPad, so you're lucky that the class is mostly on dry erase board. But I guess the good thing is that at least you can rewatch this video as many times as you need to get everything you need. So recall that delta E, or the change in energy, or the difference in energy, right, between the alpha and beta states is very small, minuscule, right? On the order of a fraction of a calorie per mole. Remember when we were talking about the energy differences in UV vis and the surrounding electromagnetic radiation? Those energy differences were in the hundreds of kilocalories, right? But here we're at a fraction of a fraction of a calorie per mole, right? So that's tiny, tiny energies, right? Minuscule energies compared to everything else. What that means then is that we can define a Boltzmann population. If I could spell population right, population, right, of the alpha and beta states. The alpha and beta states. PChem, come back in here. Thermodynamics, right? Boltzmann population. So you should remember that from PChem, and how different you can have different microstates and stuff like that, which are all the possibilities of the different states of all the particles, right? So this is what we're doing here. And so what we can then do is get the Boltzmann distribution. Using an equation, right, that involves the Boltzmann constant, right? So here we'll have NB, or N beta, right, the number of protons in the beta state, over N alpha, which is the number of protons in the alpha state, right? This equals E, right, E to the negative change in energy, right, divided by the Boltzmann constant, right, times little t, which is temperature, right? So let's just define those real quick so no one's confused. This is the Boltzmann constant. I'm having trouble spelling it now. Constant. And this is the temperature. And the temperature is most commonly room temperature, which is 298 degrees, right? So using this equation, we already know what E is, right? That's a button on the calculator for our constant. And then we know what our temperature is. It's room temperature, so 298 K. We also know what the Boltzmann constant is. So how do we figure out what the change in energy is, right? Well, if you recall back from the lecture that we gave, a couple days ago, we have the equation, the change in energy equals Planck's constant times the frequency, right, or nu. And so, if you recall, in the previous lecture too, we had related this particular equation to the magnetogyric ratio, right, which was Planck's constant times gamma, which is the magnetogyric ratio, right, times the magnetic field strength, which is B naught, right, and then all that is divided by 2 pi, if you remember that from the previous lecture, right? So let's just define all these terms real quick. Gamma is the magneto, there we go, gyric ratio. And then this here, B naught, is the magnetic field strength. It's magnetic field strength, right? So what we can do is we can put it all together, right? We can put it all together where we substitute the change in E right here, delta E here, with this equation, right? So let's do an example, right? For a if we had a 70,500 Gauss magnet, right? This corresponds to, if you were to do the math, it corresponds to a 300 megahertz instrument. Not the biggest, but still pretty good. 300 megahertz instrument, right? Actually, I think it's supposed to be a big H, right? Whatever. Megahertz, you know what that is, right? And it's at room temperature. Right, at room temperature. What is the N beta over N alpha, right? So let's do this, right? So N beta over N alpha, right, equals E. Now this is where we plug in this part of the equation into the change in E, right? So it's E to the negative H gamma B naught, all divided by 2 pi, all that divided by the Boltzmann constant, and the temperature. Pretty easy, right? So that means then that it's going to be E, right, to the negative, and that would be for, one second here. That would be for the Planck's constant, which is 6.63 times 10 to the negative 32. 34. All that multiplied by the gamma, right, or the magnetogyric ratio of, let's do a proton, and the magnetogyric ratio of a proton, or gamma of a proton, is 26753, and I gave you all those values in the previous lecture, right? And then we have the strength of the magnet, which is 70,500 Gauss, right? And so just in case you don't know what this number is, this is the gamma of a proton, or the magnetodrag ratio of a proton, right? Yeah, that's right. And so all that, right, is still going to be divided by 2 pi, right? And then all that is divided by the Boltzmann constant, which is going to be 1.38 times 10 to the negative 23, right? And that's times the temperature, which is 298 K, 298 Kelvin, right? So I'll give you a few seconds to do that math, right? While I go back and look and make sure I have the magnetodrag ratio of the proton correct. Yep, I have it right. And so I hope you did that math. I gave you some time there. We get then that N beta, or the number of protons in the beta state, over N alpha, or the number of protons in the alpha state, equals, the ratio of them equals 0.999, four nines, right? Yeah, 9952. And so that might not mean much to you, right? But I can put it in more perspective by writing out like this, where that is out of almost 2 million protons, right? 999,952 protons are in the beta state, while a million are in the alpha state, right? So what this means then is that, so there are, I don't know why that word got messed up there, are only 48 more protons in the alpha state out of oopsies, don't need that there, approximately 2 million. All right, 2 million protons. That's super small. It's a very small difference. Very small difference. So what does this mean practically? What it means practically is that when we're trying to do an NMR experiment, right, and we have, say, 2 million protons, and we have applied a magnetic field to the protons, right, they will line up, like we saw before, in either the alpha or beta states, right? And when they do that, the ones that are in the alpha state that have a partner that's in the beta state will cancel each other out. There will be no net magnetization there, and so we can't really detect a signal from those guys, right? The only ones that we can detect is the few that are left over here that are still in the alpha state. And in this case, with a 300 megahertz magnet, there's only 48 of them that are left over that are different. We call it the differential population, right? That are available for us to actually detect. And that's not very many protons out of 2 million protons, right? And so inherently, that's one of the reasons why NMR is so insensitive. Is because it's such small availability of particles or protons to be. It's not just protons. I guess you could say nuclei, to be available for actual excitation using the RF pulse. It makes it so that it's very difficult for us to be able to detect anything, because the insensitivity due to the lack of protons or the lack of nuclei. It's the differential population is very, very small, right? So based on this equation right here that we just did, what is one thing that we could do to make the differential population bigger? Well, notice that the magnetic field strength up here is up in the numerator, right? And so one way to increase because you can't increase the magnetodrag ratio. That's like a constant for each nuclei, right? And so the easiest thing that you can do, right? You can't change the constants. The easiest thing you can do is actually increase the field strength of the magnet, right? And so if, say, for example, if, say, for example, we increase the field strength of the magnet to 500 megahertz, right? So if we had a 117,500 Gauss magnet, that actually corresponds to a 500 megahertz instrument, so a little stronger, right? Uh, and we did the calculation, our n beta over n alpha would actually equal to 0.0, no, sorry, 0.9999, four nines, 19. And so now that's out of, if we put that over 1 million like we did up here, 9999, and then 19, all over 1 million. I'm only using these numbers to make it easy math, right? We now have, using a 500 megahertz instrument, we have 81 protons that are in the differential population out of out of 2 million. So the bigger the magnet, the stronger the magnet, the bigger the population that can actually be detected by the NMR experiment, right? So let's visualize what this looks like, and we've already seen this before in the other thing, in the other lecture, right? But let's just visualize this again, just to be sure that we know what we're talking about right here. Here I have E, and then down here I have the alpha state, and up here I have the beta state, right? And then imagine that we have 4 protons in the beta state, and we have 5 protons in the alpha state, right? And when you apply the magnetic field to the sample, right, the spin flipping, right, well, there will be an equal chance of having, you know, things being flipped to the B state or things staying in the alpha state. And if they have 1-to-1 match, right, they will cancel each other out, and so that will be no net magnetization. So really, the only one we can detect out of these protons here is this one proton here that doesn't have a match for it, right? That doesn't have a partner for it. And when it gets flipped up to the beta state, we can actually detect that, right? And so it becomes looking like this. Alpha state, beta state, right? And then now we only have 4 protons here in the alpha state, the lower energy state, and the beta protons, or beta state protons, there are 5. And again, we have this 1 proton here. That's the differential population that we can detect, right? So let's write all this out in words now. There is an equal chance, or equal probability, of both excitation and emission. So there is no net magnetization. We'll use that word a lot, right? Except for the one extra alpha state proton, right? Sometimes when we talk about net magnetization, we can also talk about it in the context of absorbance, right? Because again, the protons are absorbing the radio waves, right? which is electromagnetic radiation, the weakest of them all. And after the magnet has already uh, made this alpha beta population thing state occur, the one extra one will either be excited or relaxed, right? And if it's going to get excited, it gets excited because it absorbs the RF radiation, radio frequency radiation from the RF pulse that came from the RF coil, right? And so sometimes people refer to this net magnetization as an absorbance, right? Yeah. So just a couple more notes here. This is one of the reasons why NMR is so insensitive. And then the last for this section, the last note here is that, which is what you should already know, and I said it already, is that the only way to increase this differential is by increasing the magnetic field strength. Right? And again, the biggest instruments we have these days are in the 1 to 1.2 gigahertz. They're rather huge. These instruments are literally pushing the limits of what NMR can do with electricity and the limits of physics, the limits of physics and resistance and conductivity. And so that's why these things have to be so big and they're so cold and stuff like that, right? So when we describe the relaxation, right, of the proton from the beta state to the alpha state, it doesn't just come back down, right? It actually does this thing called precession. So the next thing we'll talk about is called precession. Precession, okay? Which is PRE, and then C, right? And then E again, and then SSION. There we go. That looks like an E, right? So let's first talk about the physical approach to this, right? Right, the physical approach, or the classical physics approach. Right, the classical physics approach, which is interesting because NMR was actually developed by physicists, right? And what the reason why they developed it is because they were trying to find like this fundamental constant for protons, and so when they did that, they actually realized that hey, a proton's like constant. A fundamental constant for the proton is actually not constant at all because it gets affected by like the its chemical environment, like its electron shielding and all that kind of stuff, and what other atoms it's close by and nuclei it's close by. And so the physicists actually like dumped in the NMR nuclear magnetic resonance as something that was useless because they couldn't define a fundamental constant out of it, and so that's when chemists actually picked up the phenomena of nuclear magnetic resonance, and was like, hey, this is actually super useful because we can predict what the proton is connected to, or any other nuclei is connected to in the realm of an atom to a molecule, molecular structure, because they'll have different frequencies for their environment, their different chemical environments, right? And that's actually where the term chemical shift comes from. When you talk about an NMR spectrum, and we talk about, we have chemical shifts in the 8 or 7 or whatever, or 3 or whatever, right? ppm. That's where the phrase chemical shift comes from. And so it was pretty cool because, like I said, physicists discover this phenomena, and they were like, so useless because there's no constant. But then the chemists took it and was like, man, this is a very powerful thing to use. And so now chemists use it all over the world to elucidate all kinds of fun stuff, right? So in the physical approach, let's draw out our axes again, where we have the z-axis here, the y-axis here, and the x-axis here, right? And imagine then that my RF coil, the one that was around my sample, right, is about the x-axis, right? It's coiled around the x-axis. So here's our RF coil that's coiled around the x-axis, right? And again, don't forget that our magnetic field strength, B naught, is in line with the in line with the z-axis, okay? And so, what exactly is precession? Well, precession is, and I have a couple pins here to kind of show you, is that whenever a proton, right, is in a certain state, right? So, for example, if it's in its alpha state, right, it's pointed upwards, right? And then when we pulse it, well, it will switch inside the magnetic field. Most of them will cancel each other out when they align either with or against the magnetic field, right? Most of them will. But then the differential population, which is what we care about, will be still in the alpha state, right? And then when we pulse that one differential population, if it's one proton, or it could be many protons, right? Like all, you know, which is just to make it simple. Let's just say there's one proton. When you pulse it, the proton actually turns perpendicular, right? And you would think that whenever the proton relaxes, it just goes straight back up and at being like this, right, vertical with the z-axis again, right? But it's not, and so that's kind of a counterintuitive thing, because when you talk about like electrons, that they get promoted to higher energy levels and they come back down, and they're still kind of like in this z-axis orientation. But for protons, when you pulse them, right, and they move from the alpha state to the beta state, they actually go perpendicular. And then after they go perpendicular, right, they start to relax back to the alpha state, which is in alignment with the z-axis. But they don't just go back, like straight back up. What they do is they actually spin around like this, and that's called precession, right? That's called precession. They're spinning around like this, right? And they'll spin around all the way until they run out of energy, and they return back up to in alignment with the z-axis, and now they're in the alpha state again, right? So that's what precession is. So we can imagine seeing two protons like this precessing around in a circle, like so, right? And so since you have two vectors here that are like opposite each other precessing, they actually cancel each other out. And so you end up with no net magnetization, right? So with this particular picture right here. So, but you'll see what happens in a second when we do have net magnetization. So precession of differential population spins they have a net magnetization right? It's in the z-axis. In the z-axis, right? Not in the XY plane, right? Not in the XY plane. So let's just remember that, right? When you have an alpha state proton, right, its net magnetization is going to be in alignment with the z-axis, right? And so we can draw this out in a very cartoony way here. We start out with our alpha state proton right there, with a net magnetization that's in alignment with the z-axis, right? and then we pulse it with an RF pulse, a radio frequency pulse, right? And what happens is that it comes down and it points perpendicular, just like I was showing you with the pen. So now the net magnetization right is in the XY plane. To make it even more clear, let's draw our axes again. And again, this is the Z, this is the X, this is the Y, and then we have our RF coil right here doing the pulsing, right? RF coil doing the pulsing. Although that didn't look like the word coil, so I'm going to write that again. There we go, RF coil doing the pulsing. And so we have our alpha state proton, right? And after the pulse occurs, it will go downwards, perpendicular, like this, in the XY plane. Okay? So, interestingly enough, right, I talk about only doing one pulse, but that's kind of a lie because in modern instruments, we actually do four pulses. Like, so for example, whenever you go, and I don't think we do this with our NMR, the 60 megahertz, but especially we do this with the bigger instruments. Whenever one of the criteria or parameters you have to enter when you do an NMR is you have to type in the NS, which means number of scans. And the number of scans is always in multiples of 4. Why is it always in multiples of 4? Because this is a thing that's called phase cycling. It's called phase cycling. And what are they? This is pulsing, or pulses, rather. Pulses are normally applied in multiples of 4. One in the X, the positive X, one in the negative X, one in the negative Y, and one in the positive Y. I don't know why I changed the order there. Who cares, though? It's all the same. Let's just make it positive Y and one in the negative Y direction, right? And this is for minimizing. This is for minimizing noise and maximizing signal. Maximizing signal, right? Maximizing signal. So this is the physical approach to the precession of a proton, right? So now let's do the quantum mechanical approach. Right, the quantum mechanical approach. So in the quantum mechanical approach, was also known as spin dynamics. I have a whole book just that is titled Spin Dynamics, right? We start with the different states, right? So again, we have the alpha state and the beta state, which we should already know. I'm probably not going to write it a gazillion times here, right? And say we start out with 4 protons in the beta state and 6 protons is that 6? That's only 5 in the alpha state, right? If we were to give it a 90-degree pulse, so the RF pulse, we'll say it's a 90-degree pulse, or a pi divided by 2 pulse if you're into radians, right? What happens is that we get an equalization, right? An equalization of the population, and there's no net magnetization. The one of the alpha state protons will end up in the beta state, and now we have 5 and 5. So 5, 5, 5, 5. I just counted to 5 using the number 5. That's really weird. And then 5, 5, 5, 5, 5. I just did it again. Anyway, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? And so what you see here is we have equalization of the population. And no net magnetization. Excuse me. No net magnetization, right? So we're not going to see a signal from that particular situation. So you're going to see that it depends on the angle of the pulse that we do, right? Whether it's 90 degrees, 100 degrees, right, 180 degrees. Usually it's always somewhere between. It's not exactly ever 90. It's not ever exactly 180. It's always something in between, right? So we do have some net magnetization, but I'm just kind of giving you an example here. Um, and then so let's do, if we had, for example, then I just mentioned 180 degrees and a 180 degree pulse, alpha state, beta state. Oop, set that backwards and even run it backwards, right? This time, let's say we have 4 protons in the beta state and 6 protons in the alpha state, just like before. And again, I'm just doing this very cartoony drawing, right, of the different spin states for you to show how the angle, right, of the pulse dictates our net magnetization. So we, for example, then used a 180 degree pulse, or for you guys who are into radians, pi pulse, we end up with actually everything just switching places. It looks like it, because now we'll have 6 protons in the beta state and only 4 protons, right, in the alpha state. So we definitely do have net magnetization here. I think it just put shun twice in magnetization. Sorry. There we go. Magnetization, net magnetization here, but it's along the negative z-axis, right? So it's kind of very intuitive, because you do 180 degrees, and what happens? You just point a different direction, right? Like the opposite direction you were pointing before, like you were on the other side. So it's pretty cool. Pretty cool. So, right, we're still continuing on here. If we were to have if we were to draw out our axes again, sorry, that one doesn't look as good as the other ones I've had. X, Z, and Y, right? And the coil is right here, right? The RF coil, right, is right there. And so we begin with the proton aligned with the z-axis, right? And then we pulse it, and it comes down here, right? It comes down here in the xy plane, right? And so this would be our net magnetization. Right, that's our net magnetization. And then, once it's there in our net magnetization along in the xy plane, again with our coil right here, our RF coil right there, the proton that's in the XY plane now will start to rotate about the z-axis like so, right? And that's called precession, right? And the really interesting thing about that is that remember that the RF coil not only acts as the thing that delivers the pulse, but it also will record or detect the signal or the current being produced as the proton precesses. And how does it do that? If you imagine that I am the RF coil sitting right there on the x-axis, right? And the proton that's now in the xy plane is precessing and going around in a circle like this, right? As the proton goes around in a circle and precesses and it gets closer and closer to me, it starts to induce a current that I can detect, right, in me, right? And as I get closer and closer and closer, as the proton gets closer and closer and closer to me, the current gets stronger and stronger and stronger. And then as it moves away from me, it gets weaker and weaker and weaker, and then it comes back around. When it's opposite me, I don't detect it at all, but when it comes back around again, I start detecting stronger, stronger, and stronger. When it's pointing at me, it's at its strongest, the current is strongest. And as it goes away in this circle, right, it gets weaker and weaker and weaker until it comes back in strong again, right? And so every single time the proton precesses and crosses my path, right, like my face right here, I detect a current, right? Or it induces a current inside me, and I can detect it. And so what that means then is that I, as the RF coil, detect a current, and that current is in the form of a cosine wave, right? And then the amplitude is, or the highest parts. I don't want to call it the amplitude, but the highest parts of the wave are where they're getting very strong, or because the current's getting very strong. That's being induced because it's the protons precessing closest to me, and then as the wave goes downwards, that's when the proton is precessing away from me, right? And that's why we get a wave. This wave is in voltage, right? That comes from an induced current by the precessioning proton, right? And then this axis is time, right? And like I said, it produces a cosine wave. Not a consine wave, a cosine wave, right? A cosine wave. So let's put all this together now. Um, First thing to say is as the proton with a net magnetization I always spell magnetization wrong. You can just look it up later. Precesses or rotates about the z-axis, it induces a current as it approaches the RF coil. All right? And then so the rate that the proton is precessing, rate of precession, all right, and thus its frequency is equal to the nu for the proton. And lastly, for this particular um, section, the amplitude is dependent on the difference in population. Depends on the difference in population. So again, the bigger the amplitude, right? So the more differential, the more there is in the differential population, the more protons there are, right, that are available for being pulsed by the RF pulse, right? The bigger the amplitude, and the bigger the amplitude, the easier it is for us to detect, right? And that's important. Okay. So now that we've figured out that what precession is, and the fact that precession produces this cosine wave right here, right? How do we turn this cosine wave into a readable NMR spectra? Because these waves are not, they don't tell me anything, right? They just say there's a current there. It didn't tell me that there's like, a methyl group there, right? So how does it do that? How do we turn the cosine wave into uh, a NMR spectrum? Well, the way we do it is by using a Fourier transform. And so our next section is Fourier transform. Right, a Fourier transform. Okay, so let me do a few examples here, and we're almost done with this particular lecture. Right, let's say we have a plot here, and on this plot we have 0, 1, and 2. This is time in seconds. Right, and then over here we have the amplitude, like of a wave. Right, and then right here at 0, we'll have 0 there, and then here we'll have -1. Oh, sorry, +1, and here we'll have -1. Right, and so let's draw a wave that is 1 cycle per second, or a 1 hertz wave. Okay. All right, so now we have a 1 hertz wave, okay? And so the big secret here, right, is that about Fourier transform is that all it really does, and I told you this before, but I want to reiterate it now, is all that it really does is that it's a mathematical operation that will transform or convert the time domain on the x-axis to a frequency domain, right? And so what does that look like? Essentially the same thing, right? But now on the x-axis we have frequency, right? And we'll start off with 0 over here, 1, 2, 3, right? 1, 2, 3, 4. I kind of messed up the spacing there, but just imagine that it's the same spacing throughout. And since we have a 1 cycle, right, per second wave here, or also known as a 1 hertz wave, right, for frequency, when the Fourier transform applies its mathematical operations, we get a peak at 1, right? Frequency of 1. So the Fourier transform literally just changes the wave into a time domain, from a time domain to a frequency domain. So now the graph tells you what the frequency is instead of showing you a wave in time, right? Which is super helpful because each proton will be in a different chemical environment and it will have a different frequency. And when it gets transformed, when the wave in the time domain gets transformed into a frequency domain using the Fourier transform, you start to get different peaks at different chemical shifts based on the chemical environment of the proton. It's kind of cool, right? So let's do another example. See, we have a different type of proton now. Again, we are doing 1 second here, and 2 seconds, and 0, time in seconds. This time though, and again, this is very simple, right? Because real protons are way more complicated, or way more complicated numbers. We're just using easy numbers here to make it, easy math, right? Again, so we'll have amp here for amplitude, and then in the middle we'll do 0, and then 1 and 1, -1, right? And this time we're going to have a proton that's precessing at a rate of 2 cycles per second, right? Or 2 hertz. So here we go. See if I can do this right. Oh, dang, that's really good. I'm impressed with myself sometimes. And so now, if we do a Fourier transform, where do you think that the peak is going to show up when we do a Fourier transform? Well, you guessed it. I kind of made that a little too long, but that's okay. We'll just start with 0 being there. 1. Oop, I messed up again. That should be 1. 1, 2, and then 3, right? That doesn't matter. Don't worry about the 4 there. My thing's definitely off scale, but that's okay. And so now, what do you think the peak will look like here when you transform, use a Fourier transform to convert time to frequency? Well, we have 2 cycles per second here, right, or a frequency of 2 hertz, which means that the Fourier transform would show us a peak right at 2. Now you see how simple that is. And now you can even imagine if you had more than one proton environment in a different, more than one, sorry, you can imagine that if you had more protons and each of them were in a different environment, they would have different cosines, right? Different cosines of different cosine waves of different frequency. And then when you do a Fourier transform, each one of those shows up as a peak, right, at their frequency, right? And that is essentially what your NMR spectrum is that you see when you do an NMR spectrum, right? When you take an NMR sample. Oops, I unplugged my laptop. Let me plug that back in. Okay. All right, that was pretty cool. So these here, right? These here were just like these examples here were like just singular protons, right? That were different types. Single type of proton. Right? And so, unless you're doing something like a methyl group or just a methyl by itself, like a methane that just has one type of proton, right? Then you're never going to see just one peak like this, right? It's going to be multiple peaks, right? So, let's say we have 2 protons on the same molecule that are 2 types of protons in the same molecule, say like a methanol or something like that, right? You have the methyl protons that's on the carbon, and then you have the proton that's on the oxygen. Those are 2 different types of protons in 2 different environments, right? So what would that look like? What would that look like? Well, again, we'll draw out our little thing here where 0 is here, 1, -1, right? And this is amp. Okay. And so we'll draw 1 proton. I forgot to draw the x-axis. Sorry, we need to do that too. 1, 2, right? There we go. And so let's do 1 proton as a 1 hertz proton. And then let's do another proton that's a 2 hertz proton, or 2 cycles per second proton. Precesses at a rate of 2 cycles per second. All right. And so that's essentially what that would look like. Okay. I'm sorry, it should be more straight down there. Right, the amplitude should remain constant with both waves, but I apologize. So what will happen then is that you have now 2 waves overlapping each other, right? And if you recall back from the very first or second lecture, I was talking about the superposition of waves. Remember that? They sum up. And you end up getting a wave, a sum wave, right? That looks a little something like this. So now we have 0, 1, -1. And then up here we have 2. And down here we have negative 2, right? And so now we'll get the sum of it, the sum of the wave, right? And we'll get the sum of the wave, of those two waves, those two cosine waves, which looks a little bit like this. Sorry, this should go all the way down here. Like that, right? That's the sum of those two waves. And so, I forgot to draw the x-axis, so that's 1 second. And then that's 2 seconds right there, right? And so this is the sum of the different frequencies. Right? The sum of the different frequencies. So after we do the sum, after the computer does the sum of the different frequencies, we do a Fourier transform. And it's able to deconvolute this sum, right? Because you by yourself wouldn't be able to do it. You would just see a whole bunch of overlapping lines, right? Because there's so many different types of protons on a particular molecule sometimes that all these lines just overlap with each other. You can't tell the difference. What the Fourier transform can, and it will deconvolute this, like, this sum of the different frequencies into something that's usable. So here we have our frequency domain again, instead of time domain. Right, again, this is time still. Time in seconds. And this is also still time as the axis in seconds, right? Now we have frequency over here after the Fourier transform. And we'll do 0, 1, 2, and 3. Right? And so now it can deconvolute this thing, right? This sum of the frequencies into a peak at 2 frequencies. I mean, sorry, 2 hertz, and a peak at 1 hertz or 1 cycle per second, right? And so now you can imagine if you had a molecule that had a whole bunch of different, again, a whole bunch of different protons on it, or different types of protons, in different proton environments, chemical environments, they would have a crap ton of overlapping cosine waves that represents their individual precessions, that induces the RF current, right? Or sorry, that induces the current in the RF coil, right? And all those different cosine waves would like overlap on each other, becoming this big jumbled mess of lines, and you would never be able to know what it is, right? And they all get condensed into this sum of all of the different frequencies. And so the magic is that the Fourier transform is this mathematical operation that can deconvolute all of that data, right, into giving you very useful information, like all the frequencies that are available within that. That summation of all the different frequencies. And so, we'll just write one thing here. A Fourier transform. So that's a capital letter there. Fourier transform is a mathematical operation Does mathematical have an E in there? I don't know. Whatever, I'm Asian. Operation that converts the time domain into a frequency domain. My lights over here are freaking me out. Like, the RGB keeps on flashing red back and forth, and it's really freaking me out. All right, so let's talk about our last couple of things here, right? I kind of lied a little bit, right? Because when I drew you all the different cosines waves, they looked like they were infinite, right? which means that they just keep on going forever and ever. But in fact, they don't go forever and ever. They actually decay because eventually the proton is going to have to return back to its z axis alpha state, right? So the next topic then is called the free induction decay. Also known as the FID. A lot of people like to call it the FID, right? Not to be confused with the FID as in like what is it called? The flame ionization detector. This FID is the free induction decay. So let's talk about first. What if you had a cosine wave that continues infinitely, right? So the what that means is that the proton is precessing and it just keeps on precessing forever. It will never return back to the z state, the alpha state that's aligned with the z-axis. It just keeps on spinning forever and ever and ever. What would that look like if the consine, what the heck? Cosine, I just wrote con again. The cosine wave continues indefinitely or infinitely. That probably means the same thing, right? Indefinitely, infinitely, whatever. Right? Let's draw this what this would look like. And so here's my cosine wave. And I'll just have the node right there. Right? And what I'll do here is that we'll do dot 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 to kind of represent that this keeps on going forever. And if you did a Fourier transform on that particular cosine wave, what you end up getting, right? And again, this is still a one cycle. One cycle per second. 1 cycle per second wave. You would get a, let's make our 0, 1, 2, 3, right? You would get a peak or a line at 1 hertz. But the thing to take note of here is that since the cosine wave is like going infinitely, right? You get an infinitely sharp line. It doesn't even look like a peak, right? It doesn't even look like a peak anymore. It just looks like a sharp line. But in reality, though, is it like that? I mean, you guys tell me. You've all done NMR with Dr. Pelfrey before. Are the peaks that you see in the NMR spectrums, are they infinitely sharp like this? Well, the answer is no, right? And the reason why is because in reality, there's this thing called relaxation. Right, this thing called relaxation. And again, just so we're still caught up with everything here. These protons are spinning, right? They're precessing, rotating around about the z-axis, right? But eventually they're going to run out of energy, and they relax. And when they relax all the way back to being in alignment with the z-axis, right? And so that's called relaxation. Okay. So what does a cosine wave look like for something that has relaxation in it? Right? What does it look like? Well, it looks like a cone, actually. It looks like a cone, right? And in this cone, or in this manner, we have what we would refer to as exponential decay. Right? And so when you're doing an NMR on the screen, right, an NMR on the computer screen, you'll see this thing that's an exponential decay, also known as a free induction decay or a FID, right? But it never looks like that, like one wave. Why is it? I mean, you already know why. It's because you're doing an NMR on a molecule that has multiple types of protons in different environments, right? And so all those free induction decays for each of those protons that are like this decaying cosine wave are all stacked on top of each other. So that's why it just looks like a fizzy cone, right? Fizzy, zigzaggy cone, right? So what you would see in the what you would see in the free induction decay of an actual molecule and not one molecule that just has one proton, right, is something that looks like this, right? Make this look a little bit better. This is starting to look like those free induction decays that are actually on the instrument that look terrible. All right, that's a free induction decay, right? And the decay occurs exponentially. Okay, and so you can imagine that once you get down to this point over here, where there's like no peaks anymore, right? That's where the proton has essentially uh, reverted completely back, precessed all its way, all by itself all the way back to being in alignment with the z-axis again, right? So what happens when you do a Fourier transform of of a FID? Ft of a FID, right? What does it look like? Well, we get a peak that is much more realistic. And that peak is what we would call a Lorentzian line shape. So 3, 2, 1, and then 0. And we only have uh, one type of proton here going 1 cycle per second. So now we have what would have as a much more realistic peak shape, right? And this is known as Lorentzian line shape. Lorentzian line shape. Okay, I can write the word shape, I promise. There we go, Lorentzian line shape. Okay? And so again, that's much more realistic to what you would see when you're taking an actual NMR of a molecule, right? And the FID that you would see is much more like the one that's down here, right? Not like this, because very rarely do you only have one FID. There's always a crap ton of different types, environments of protons all stacked on top of each other. And so it just looks like one solid cone. Sometimes when you're doing an NMR and you get a really weird looking FID, right, then something's going wrong. It should always look like this. Something's gone wrong. So the last thing I want to talk about then in this lecture is called relaxation, because I mentioned it just now, right? Relaxation. There are two types of relaxations in respect to with respect to precessing and protons and such, or nuclei in general, which is actually kind of ironic because the two types of relaxation are actually the two types named after the two types of waves, which are the longitudinal waves and transverse waves. So this is called longitudinal relaxation and transverse relaxation. So let's first talk about longitudinal relaxation. This is sometimes called spin lattice relaxation, or sometimes called T1 relaxation, right? In fact, it's probably most commonly called T1 relaxation. What is this? This is the re-equilibration of alpha and beta spin states through the transfer of energy and thermal motions of the sample. Through the transfer of energy through thermal motions in the sample. Right? So this is probably the easiest one to understand because this is the normal type of precessing where it's spinning around in a circle, right? Like about the z-axis, and as it's spinning, it will eventually return back to being upright in alignment with the z-axis, and that's what this is, longitudinal relaxation. It's the one that we know of, that you're the most familiar with because I've been talking about it the whole time, right? Where the proton spins around in a circle until it starts running out of energy, and then it will eventually precess all the way back to being in alignment with the z-axis. That's literally what the longitudinal relaxation is, right? So if we want to visualize that, it's something we've already drawn before, right? And here we have our proton right there, right? That's in the xy plane, and it's going to go back up to being in alignment with the z-axis, right? Which means it's relaxed now in the alpha state. That means we have lost our net magnetization. We've lost our net magnetization, right? But it's okay though, because we can just pulse it again, right? But now it's going to be relaxed back into its alpha state, which is in alignment with the z-axis, right? All right, cool. And then the last type, like I already, what I alluded to a second ago, is known as transverse relaxation. Surely I can read this right. Relaxation. There it goes. This is also known as spin-spin relaxation. Or also known as T2 relaxation. Right? So actually it's probably most commonly known as T2. So T1 and T2 are very common numbers, or not numbers, designations for this type of relaxation. NMR instruments use that, right? So what is this? This is the interaction of spins with other nuclei leading to unbunching of spins in the xy plane, resulting in a loss of net magnetization. So what does unbunching mean? Well, you can imagine if you have more than one type of proton and they're precessing about in the z-axis, right? They might start out together, right, as they both get pulsed at the same time, but then one starts to lead and the other starts to lag, and one is going to be going faster than the other, and that's when they start to spread apart like that. That's called unbunching, right? And so to draw that, we can show two protons that start out together, right? And as they go around and precess, right? As they go around and precess, unbunching occurs because of interactions between the spins and the nuclei. Unbunching. And then, so we end up with one of the protons over here, right? And then the other proton is over here, right? And that results in the net magnetization, loss of a net magnetization, right? All right. Well, that ends part two of the concepts and the basics of NMR spectroscopy. When we come back on Monday, I'll go through some easy very easy to decipher NMR spectra and how to decipher NMR spectra. And then after that, we'll start doing mass spectrometry, right? It's kind of amazing because our class is almost over. It's so sad. I'm going to cry. But it's been a good semester, all right? So if you have any questions, let me know, and I'll see you back in class on Monday, and be on the lookout for an assignment that I post, okay? Good job. Have a good weekend.